Okay, welcome everybody. My name is Dawid Luczyniec. I'm one of engineers dealing with out-of-Earth manufacturing in European Space Agency. If you will have any questions after the presentation or you will want to work with us, you can contact me or my colleague or anybody at ESA using the template name, surname at esa.international or .int. Okay, so maybe first to introduce myself, I'm originally a foundry engineer. So I started my career as a semiconductor foundry metallurgist. So I specialized in that. I then moved to American corporations with jet engines production. Then I moved to rocket production, to nuclear propulsion, and I ended up in ESA as a launcher material engineer. So as an introduction, what is ESA? What is European Space Agency? So it's international organization. So unlike NASA or Swedish Space Agency, we are international organization which works similar to NATO. So it's not one country bound, but we work on behalf of 23 member states, also on behalf of Sweden and other European countries, plus Canada. So in general, there is now over 6,000 employees, mainly engineers. And what is important to know that unlike NASA, we do not make our own stuff. We usually give the opportunity to the companies, to the startups, to introduce certain capabilities. And what we do with it, we make it usable in space. So this is the basic mandate of the organization. So we try to introduce such technologies for exploration and use in space, exclusively for the peaceful purposes. This is our main mandate. We have a headquarters in Paris with seven different locations across Europe and the spaceport in French Guiana. This is the 23 budget, I think. So it's almost 8 billion euro. So if you calculate it per one European citizen, you can say that from your payslip, you spend €1 a month as a let's say a subscription fee for having such capabilities. This is the nice map with all the countries. So the white countries are members, the gray are cooperating states. Okay. Those are the locations. I'm originally from ESTEC or ASTEC, which is in Netherlands, south of Amsterdam. And what we do, those are examples of which projects we do. So we introduce Copernicus, which is Earth observation satellite, maybe constellation, we can call it this way, but it monitors, for example, how the warming or how the climate affects the rise in the sea levels. So as you see, since 1990, I think it was plus 9.1 centimeter of the water rise. For the Dutch people, it's a sensitive topic, yeah, as you know, since they are mainly below the sea level. We also introduce or operate Galileo. So if you use anything which needs precise geopositioning, this is the type of the satellites we introduce. So it's used in cash machines, smartphones, TVs, radios, navigation, any kind of weather alert regarding the yellow storm warning. This comes from this capability. We also do quite a lot of science. So we operate, for example, Planck satellites, which looks into deep parts of the space. We had in 2014 Rosetta missions, where this was the first spacecraft which landed on a comet. We also developed European Service Module, which is part of the systems which delivers different media to the Orion spacecraft. We also operate space debris monitoring system. So this is a set of telescopes which monitor all the debris which we, as humanity, left on the orbit ourselves. And also we monitor any foreign object which, let's say, approaches our planet. So this is probably the closest capability you can get if it comes to like Hollywood movies. We operate Ariane 6, so we supported the development of the launcher. We also currently developing Space Rider, which is a reusable small shuttle, which will fly on Vega C rocket. So we developed the Rosetta mission. We also have a full capability to test those spacecrafts. Yeah? So, for example, if you develop a software spacecraft or anything which intends to fly in space, but you, for example, don't have the necessary testing capabilities in-house, we usually deliver such capability. So me personally, I'm coming from material structures and mechanisms section. So we actually calculate, design all the hardware which intends to go to the mission. Yeah? So it's starting from the satellites, the rockets, the main structures, the materials. We test the materials, we test the structures. We do flight acceptance. So we go through whole documentation which comes from different companies, and we kind of filter that through sanity. Yeah? We also now started to engineer our hardware as a design for the DEMIS. So we want the hardware to burn in atmosphere or the orbit itself after some time, not to trash the orbits. So if it comes to out-of-Earth manufacturing itself, so the general vision is that we will have something on, for example, the moon. We will send there people and astronauts, let's say, will need something immediately, which they haven't took from Earth. So the intention is that they will contact the center. There will be some kind of autonomous system which will design the part, predict what's actually is needed to realize the function. So let's say a shovel, yeah, on the moon. It will be auto-designed, and using we will put on the surface of the moon actual manufacturing facility, which will autonomously print, let's say, maybe use different method of production, this part and deliver it autonomously by robot to the astronaut, using the resources which are on the moon, which is basically a dirt. And why we bother? Yeah? So in general, for the space industry in a whole, there is a couple of limitations. The main one is size limitation. So you cannot. You have to always think about what you can put on top of the rocket. Yeah? So you cannot put there like a house. Yeah. So you have to fold it, or you have to assemble that on the orbit. You have to design for the launch load. So the acceleration during the launch can destroy very flimsy or very delicate parts. So by that you over-design the geometry. You put a lot more mass than you need. when we prepare such hardware. And this elongates the time to market. So you can expect like 5 to 10 years from start of the design or your intention to put something on the orbit till actually flying the part. So if we think about future, so the human space exploration, there is a lot of waste regarding the use of the supplies which we provide on the orbit. So there is a lot of supplies which we put in the International Space Station, like you see here, which are never used. Yeah? So we kind of want to be on the safe side, so we put a lot of stuff just in case, but at the end it's not used. So if you have like a manufacturing capability on the International Space Station, you can produce something on demand. Yeah? This comes to the launch costs, which are quite high, and the further you go, the more problematic logistic chain becomes. So this is, let's say, one of the capabilities which will enable new designs. So if you look, for example, here you have like the human size. This is the James Webb, the newest James Webb size of the maximum size of the satellites, and still you had to fold it to fit it on the rocket. But with manufacturing in space, you can think about extremely large structures. Yeah? So the future successors of the Hubble and James Webb space telescopes will be far more larger. Somebody actually calculated how much waste is on the space station. So you can think, let's say, about reduction together with in-space manufacturing and recycling. You can think about almost 98% of reduction of the waste. You can think about producing, building, or printing the habitats on the moon. You can reuse the dirt or the moon dust to produce the parts. You can think about producing something which can only be produced in low gravity. I think this is one of the fiber optics, specific fiber optics cables. Yeah, and this new paradigm comes from the expectation that the space will become extremely crowded. Yeah, so we can expect a much more waste on the orbit. So this is actually the view from the detected debris around our planet. Okay, let's say the debris is over-exaggerated, yes, so it's not so big, but you can think of, you can imagine what's the number of the debris currently flying around the planet. So there is a couple of challenges. So you have to realize this capability, you have to know which process you have to use it, how to validate it. Yeah, so you cannot use the same stuff you do on Earth. You have to define those on-orbit factory stations. Okay, later standardization will come, specific designs, etc. But also, this capability has to be fully autonomous. So you will not send 40 people to, let's say, pick the part, put it in the machine, take it from the machine. Even connecting or sending information to the printer or to the factory, it does not have the same bandwidth as you would expect on Earth. Yeah? So the same systems you know from Earth do not work on orbit. So what we do now? Yeah? So we have a specific initiative in which we invited a lot of companies to work with us and to introduce certain technologies, which later on will evolve into something which can be actually used on orbit. We are not the only ones doing this in-space manufacturing or out-of-Earth manufacturing. There is a lot of stuff happening in NASA, DARPA. There is quite big initiative in UK. China is doing something, Japan, Luxembourg, South Korea. If you look on actual hardware, which is developed to make this out-of-Earth manufacturing happen, majority of the test or prototypes, they were put on International Space Station, which functions as a lab. So I think NASA was the first, and they started to 3D print a lot of plastic stuff on International Space Station. So we have to know that, okay, you have a hardware, but again, this is almost fully autonomous machine. You have a support of one astronaut, which, okay, you can put a hand inside and take out the part. But again, the whole process has to be fully autonomous. This is actually something we did in ESA. So we printed with PEEK, which is a specific polymeric material which has similar properties to aluminum and can survive in space. So we build this system and we try to print a few parts. We also concentrate on printing very long structures. So let's say if you would want to build something in space, like a structure, you need very specialized machines for that. And we started to build the prototypes. Again, we develop constantly the range of the methodologies and the processes we can produce with. Okay, we can do ground demo, so we can do like a simulated space condition, and we can test in this simulated space condition. We also invite students to fly their thesis on orbit. So let's say you do your PhD or master, and you have like a very nice idea. You can come to us and try to put your stuff in the space. Yeah, okay. This is one of the 2020 flight tests from China, and they were first to 3D print carbon fiber reinforced thermoplastic on the orbit. This is one of our activities with very, very long structures printing. So, okay, the structure is, I think, 2 meters long. We also have a ground demo of very big structures printing from CRFP. And this is one of our success stories from 2024. This is the first time metal part was printed on the International Space Station. So this is how this printer looks like. This is actual video made during the print, actual print on the orbit. This is the astronaut pulling out the specimens. So how it was done? So we started to design this mini factory with the software, hardware, etc. in 2019. We did engineering model in 2020. We qualified the model in 2023, and we launched it in 2024. So the machine had to survive the launch. Okay, so as you see, Danish guy installed the first version of the hardware. We started doing some tests in May, and we set the machine to print for 25 days the actual specimens, which are very similar to what we do on surface of the Earth. And here the guys pulls the stuff out. So we already have the parts and we are testing them. We are checking whether this is actually the same stuff we usually print on the Earth. Yeah, and this is how it looks like. Maybe it not looks, let's say, impressive if you compare like very complex parts which you usually see on in internet or in TV. But again, this stuff was done on the orbit. Okay, I actually have actual videos of the next steps. This is not yet, let's say, published or available. So now we increase the complexity of the stuff we can do on the orbit. The video, the frame count is very low, yeah, because the camera has to be, let's say, it doesn't have the frame rate like 4K, yeah, or it's not 60 FPS, rather 5, yeah. So let's say the process is quite smooth. Now we increase the complexity, so we try to be, let's say, we are testing the system, we are pushing that to the boundaries. And now you're trying to make some complex stuff, maybe a small rocket or some shape of the rocket. So we can, let's say, if a positioning rocket would break on the International Space Station, the guys on the orbit would be able to do it themselves immediately. Yeah? So they wouldn't wait 6 months or 12 months for supply of the new system from the ground. Okay, and there is a lot of stuff happening currently, which are in preparation. So together with NASA, we are now trying to weld the material during the SpaceX launch. So we have especially cracked the parts, and we will be trying to repair the part during the launch. Yeah? There is a lot of initiatives happening or initiated from within the industry itself. So I think the intention of this activity is to demonstrate some kind of ability to have factory on orbit. We also try to test more complex systems. Usually the more particles, the more messy the process, the more difficult it is to control. So all the powder-related processes or where the liquid is involved are extremely hard to control. We try to increase the complexity. So here, this is a small structure of a reflector antenna. So we try to build this structure step by step, similar to what you can have on Earth. Now the industry, or let's say the humanity, and by we I mean everybody on Earth, is trying to introduce the larger and larger structures production capability. Yeah, so as you see, the parts and the intentions grows. Yeah, so we start first with the small stuff. Now we are trying to move into meter length with the let's say new projects, which are a kind of 100, 200, 300 meters long structures on the orbit. So maybe it's not yet like a Death Star area, yeah, but there is a lot of projects which kind of aims to do that. Yeah, so there is a lot of stuff happening. Constantly new initiatives comes out. They are kind of mixed with ability to produce what you actually send from Earth. So this is a business incentive, but also in the future there is a lot of mix between this out-of-Earth production capability and resources utilization. Yeah? So you would use the data you get from Rosetta mission, which landed on the asteroid. You would, let's say, land with the space factory, and you would start to mine this asteroid. So this is the new wave in this out-of-Earth manufacturing, which occupies quite a lot of my time. So we are trying to go digital. So we are trying to transfer all the terrestrial systems, which we know work, to the on-orbit manufacturing. Yeah? So this involves the fact that you cannot use big, like AWS calculation centers, or you cannot use high-performance computing. There is no bandwidth, no power on orbit. So you have to do the same stuff you do with HPC, but using calculator. Yeah? And this is the intention. We also try to transform traditional manufacturing into the direction of how software is made. Yeah? So the traditional manufacturing is full waterfall system. So you start from A to B to Z. Yeah? But in the new system, you have to be much more adaptive. Maybe you will like print or manufacture something, you mess up at certain point, and you have to find or immediately react and do another process which would remake or reconstitute part to original function. There is quite a big, let's call it, roadmap of the methods we are trying to introduce. So majority, you can call them virtual testing or digital twin, or you can use specific words to describe certain concepts. But this involves replication of the physics. So let's say from the atom level to mesoscale to macro scale, to describe the process and the properties of the material or physical matter. And then you try to control that with some algorithms. Yeah? So I think here I call it machine learning or artificial intelligence, but basically this is some form of algorithm which gives you ability to control the process and react to unpredictable things which happen during the processing. And what is important that this is not a large-scale production. This is not automotive, where you have 100,000 parts, you generate a lot of data, you put it into neural network, and you kind of have a very nice or low error and very nice replication of the physics or the replication of what is happening with the system. Here, we produce 3 parts, yeah? Or the intention is to produce 1 part, but always right. Yeah? So we have to mix the physics and the machine learning methodologies. Okay, those are the examples of, let's say, some of the activities I did. Here we try to replicate the physics of what is happening during 3D printing from atomic level to the mesoscale. Yeah? So here, if you remember those specimens which were printed on the International Space Station, so we are trying to predict what would happen with the material or during the process as if we would be on International Space Station, but only in the simulated space. Okay, this is one of the terrestrial applications where we printed Ariane 6 engine, and we used specifically artificial intelligence or computer vision to spot immediately the defects in the combustion chamber, which is impossible to be made by humans, since each layer or each picture of the layer, which is 40 microns deep, and you build quite a big chamber, happens in microsecond. So you can generate a couple million pictures, but nobody will sit and check through every picture to check if there is like a pore or something. So this was done in fully autonomous as a fully autonomous system where artificial intelligence or machine learning with computer vision detects the defect and has precognitive capability. So it gives us a warning where something wrong is starting to happen. This is a new type of the design where we told computer to design the bracket. Yeah. So traditionally, this is a bracket like you would buy in hardware store. But what we told computer to de-weight it, yeah. So make it in a way that it's stiff as the original part. So this part, if you would fill all the pores, would have exactly the same stiffness properties or launch survivability as the fully compacted part. Yeah. And it's based on the math, which comes from the description of the hip bones. Yeah. Okay, we also built first digital twin for the tanks production. I think I have better pictures later on. And we also worked with Norwegian guys to make full embedded sensors in the electronic boxes or in the payload, which starts their life from the production. So you measure everything which is happening with your part, the location of the part, loads, vibrations, temperature, moisture, from the point of the production through the transport and on the orbit. Yeah? So you have like a full information during the life cycle. Okay, this is maybe a better view of the part with the stresses distribution. Okay, this is the digital twin we developed for the tanks production for Ariane 6. So this is kind of a big stuff. I think the machine is like 3 meters tall. Okay, this is just a GUI. Yeah, so since you're trying to deploy the system for traditional operators, which usually work with their hands, so you have to give them a chance to understand what kind of data they are capturing. So we did this in-situ monitoring system with some ability to predict with certain confidence what will happen with the part during the printing. So those are the slices of the different parts of the rocket engine. So this is this Norwegian standard digital twin initiative. And this is the newest stuff, which is now finishing. So traditionally, let's say, you can have like machine learning system which needs 20 teraflops of calculation power to actually do some kind of function on the manufacturing side. But you have to deploy it on megaflop, yeah. Or let's say the few orders magnitude lower calculation capability. So I think this transfer from available memory 80 gigabyte to 250 kilobytes. Yeah. So let's say you demonstrate like very nice pictures or very nice capability on the model with which you can apply inference on ATB. Yeah, but okay, what you have actually is 250K model. Yeah, and it's expected that it will do the same stuff. Yeah, there are different techniques. You can. You can apply, but basically it comes to the fact that you have to get away of all the unnecessary stuff in the model. So you cannot put it as is. You have to maybe you can operate on single vector only. Yeah, but still it's okay. Yeah, so you don't need all the stuff which the models usually have. Yeah, and how you can prove your ideas. If you have something you want to deploy with us, you actually can. If your entity from member states, because remember that you're paying the subscription for ability to work with us. Depending on how mature your technology is, you can apply for different, let's say, publicly open calls or open applications. Usually, if this is like a crazy idea, we can go to discovery, and this is TRL 01. I think quantum compute currently starts from that. Although I'm not doing within this initiative quantum communication or quantum annealing. We are more like quantum modeling. So we are trying to not implement machine learning on quantum computer, but actually, let's say, do like a finite element, solid mechanics calculation or partial differential equation on the quantum compute. So usually this discovery process, discovery call is quite good. If you have like something which already works for terrestrial system, so you deploy that in manufacturing, shop floor, in other industry, but now you want to transfer it to space, you can use so-called TDE, which is like proof of concept, delivery of proof of concept. If you want to give us like a prototype of working system, you go to so-called GSTP, and later on, you have to speak directly with the specific programs like ARTES or Earth observation or launchers, which will deploy your software or your system or your ID directly to the hardware. Yeah, so there is a lot of different, let's call them initiatives. Yeah. I think out of Earth manufacturing is located in so-called advanced manufacturing, together with different manufacturing techniques, and part of it in orbit servicing and construction. So, for example, part of this on-orbit manufacturing also intends to like repair the satellites. You have like a satellite which is 50 years old. It's almost dead, yeah, almost no electricity, or the solar panel is like 1990s. You will fly to this satellite, rip off the old stuff like a pit stop. Oh, yeah, this is actually quite a nice analogy. And you kind of need a lot of software to, or the system, software and hardware together working to do this capability. And the new call for quantum technologies, again, I think 90% is quantum communication with a small portions which deals with quantum modeling. Yeah. So out of this advanced manufacturing call, there is one piece which deals with out-of-Earth manufacturing, which is on-orbit manufacturing, on-body manufacturing, or resources utilization. Yeah? So this repairing called satellites is on-orbit manufacturing, building habitats is on-body manufacturing, resources utilization is like asteroid mining. Yeah, so thank you for today's meeting. Actually, we have 2 minutes. If you want to have questions now, we can do it now. I think organizers have like a separate, give us separate ability to discuss if you want to maybe work with us, yeah, in one of the calls, or you want to know more about past activities. You can approach me, and we can have a discussion. Yeah.
So in the beginning, you talked about feasibility and sanity testing ideas, but now I would like to throw your feasibility and testing out the window and think big. If you didn't have any budget limits, what would be the wildest thing what project would you want to do?
I think there is in UK there is currently quite nice project with energy transfer. So they want to build very big structure on the orbit. Okay, like 100 times bigger than International Space Station, which will generate energy on the orbit and transfer it with microwave to the ground. Yeah, so we know. Yeah, we know that technically it's possible. Physics works, okay, with 3% efficiency, but okay, the energy on the orbit is for free. And you can make dirty cheap structure. So you basically can produce all the energy on the orbit and transfer it to the ground. Yeah, and this would. Because usually in space projects the problem is with actual economy. Yeah? So you have to have a product. You have to sell something. Yeah, and if you would have like a energy which is 100 times cheap than what you have now, this would actually explode the number of the companies and projects related to this out of Earth manufacturing, but in general the space. Yeah. Yeah, okay.
One quick question.
Before you were talking about additive manufacturing with metals, do you still have problems with the structural integrity along the axis of the prints?
Yeah, but this is inherent, the inherent process issue. Yeah? So this is not forging. Yeah? So you will not have homogeneity of the properties. You will have structural issues, but the way how to deal with it is to take account for that. Yeah? So your XYZ strength is completely different. You have anisotropy, but you can design the part like you, for example, design the composite. So you just assume that the strength in Z direction is different, and you adapt for the debit in the process, and not you do not expect it to have exactly the same stuff as you get in traditional manufacturing. I think the 3D prints they are more similar to the castings than forging. Okay. Okay, so thank you for today. Hope you enjoyed that, and you will. I hope you will have a chance to work with us in one of the projects. It's completely open and to anybody. It doesn't matter if it's a student or 50 years experienced guy. Yeah, so there is a place for everybody. Okay, yeah, thank you.